Good morning, everyone. I hope that you guys are having a good start to your Thursday. I hope that you're enjoying this very last day of class. I hope that you're ready for finals. I hope that you do well on all of your finals. I've got a little bit of a preference that you do really well on this final. Um, so what I've got for you today is I've got 30 more questions that we're going to work through. Um, we'll look at them as poll questions in kind of in batches, and then we'll work through them, kind of the concept behind them, and then I'm going to do my best to kind of elaborate on, well, one way that you might see this question is, or here's a way that this question could be changed to make a little bit of a different question altogether, but with the same concept being addressed. Now, I am sorry. I have also posted a practice exam. That exam is on our Canvas site. I believe that it's untimed. I'm like 99% sure that uh, I shared it or I published it. Could anyone in the chat confirm that I shared it or that I published it? Yes, it's there. Great. Thank you. I don't think that I have a timer on that, so that doesn't, yeah. So it doesn't really simulate the exact same thing. I believe, you know what? Since you're asking, Kelly, that means to me, that means I probably, while I'm doing this, I need to go ahead and I'm going to go to that quiz because I'm guessing that means that the answers aren't released when you finish it. So let me go ahead and adjust that. Final exam practice. It's up. I don't know. Okay. Um, okay, I need to change some things. Thank you very much for bringing these things to my attention. Allowed attempts, I'm going to say 99 attempts. Um, let students see the correct answers. So after you finish it, you will see the correct answers. So and you will get a score, but of course that score is not calculating, or that score is not integrated as a part of your final grade calculation because this ends up in the assignment group known as not included in your grade calculation. Um, so there we go. But this is similar in the sense of the content that's going to be on your exam and kind of the relative distribution of stuff. Um, looking at that exam, if you go through it and you're like, hey, he didn't ask anything about this, um, does that mean that let me rephrase this. If there's something that is not on the practice exam, that means that it's a low probability that it will be on the actual final exam. So I want you to focus in on the things that are on that practice exam. Now, I'm saying that with kind of delicate wording. It's not a 100% certain that that will not be on there if it's not on the practice exam, but it's lower likelihood. The things that are on the practice exam are kind of high value things. Like these are the important concepts for the class. Um, so with that said, I'm going to go ahead and open up your first batch of questions. I've got a periodic table up so that I can kind of toggle back and forth between that. But you've got 8 questions up. I'm going to also open up a slide deck so that I can kind of jot things down, and I'll share my screen on that. So, so these are kind of dense questions, so I'm going to give you a little bit more time. And since the intent or my intent and the purpose of all of this is to jog your memory of some of these things, I'm going to kind of be working through these topics and working through the questions um, live while they're up. So, this first question, which atom must appear on the outside of a Lewis structure and never as the central atom? Okay, there's a couple of different things that you could do in order to answer this one correctly. One thing that you could do is try to think about some of the compounds that we've talked about. We've talked about CH4. Okay, if we were to draw that, it would look a little bit like this. So H, H, H. So carbon, well, carbon's not the outside atom. And the key word in that sentence is always. Okay, so carbon is out. So nobody's answered carbon. Then we've got nitrogen. Well, we've talked about NH3, and this is what that looked like. Um, okay, nitrogen always on the outside, so kind of like in the peripheral atoms, like the ones that I've circled right here. No, the nitrogen's not there. And then we've got, let's see, sulfur and hydrogen. Now, we haven't talked about sulfur-containing compounds very much, but I know that there was, I believe in a homework problem, SF6. Okay, SF looks like this. Okay, so that's an example of sulfur is not on the outside, so the always is out of the question. So by process of elimination, um, carbon, nitrogen, and sulfur are all out. So that's one approach that you could take. Another approach that you could take is, well, let's just draw a kind of hypothetical molecule. X going to Y, 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 and Y. Okay, so these X and Ys are simply symbols. Um, based on how I've drawn that, based on how I've drawn this, you can see that X has 8 electrons around it. Y has 2 electrons. Now, is there an atom that we know of that always has 2 electrons and no more? Yeah, hydrogen. So another approach to this question could be how many electrons is that atom going to be happy with? Hydrogen brings one in and it shares another with another atom. So hydrogen is your correct answer. Now, number two, total valence electrons in the structure NO3 minus. That might be a little bit difficult to see there, but that's a 3. Okay, so nitrogen, you'll have the periodic table, so you'd want to reference that. So nitrogen's rolling in with 5 valence electrons. Plus, then we've got 3 oxygens. So I'm going to say 3 times. And then if I look at oxygen on the periodic table, which I'll toggle over to my browser, and you can see oxygen is in group 6, also known as group 16. So this 6 is the same as 16, and 16 is the same as 6. That tells us the number of valence electrons. We are talking about oxygen having 6 valence electrons. So we're going to say 3 times 6. 3 times 6 is 18. And last but not least, when we have this negative sign, that means these 4 atoms have an overall negative charge. And what that means is that they basically have an extra atom. So we'd look at this, we'd say, all right, plus 1. So 5 plus 18 plus 1 is 24. Next up, which of the following atoms can expand its octet? Now, for this, I'm going to toggle over to the periodic table. And expanding the octet is reserved for a couple of different substances. And just as a little bit of a spoiler, when we talked about things that could expand an octet, we said everything from phosphorus on. So basically, what we saw more than anything was we saw phosphorus and sulfur as the 2 atoms that were able to expand the octet or their octet and have more than 8 electrons surrounding them. And I want you to use that kind of as a guiding idea and guiding principle. Sulfur, chlorine, phosphorus, they can all exceed the octet. And anything after that can exceed the octet. So chlorine, for example, could have six atoms around it. If it has six atoms around it, that means it's going to have 12 electrons that it's sharing at very least. Okay, so next question. So sulfur is the correct answer there. In the structure PF3, the phosphorus atom has one lone pair, no lone pairs, two lone pairs, three lone pairs. Let's take a look at this one. Phosphorus PF3. I'm going to write this out. And I believe that I am sharing what I want to share. I am. Okay, so PF3. This is question number 4. Phosphorus rolls in with, from the periodic table, 5 valence electrons. Fluorine rolls in with 7 valence electrons. There's 3 of them. So that would be 5 plus 21 equals 26. Okay, so when we're drawing a structure, we want to go ahead and put our central atom, which is the one that's listed first, and or the least electronegative. So phosphorus is listed first, PF3. F. Okay, so how many electrons have I drawn so far? 6. So I'm going to say that I have 20 left to draw. So I'm going to do 1, 2, because I'm completing the octets on my adjacent atoms, those being my fluorines. Fluorines always love to have 3 lone pairs of electrons. Now, just to bring back some terminology, I'm going to change colors on this. This is a lone pair of electrons. I'm going to label it as an LP. And this right here is a bond or a shared pair or an SP, a shared pair of electrons. Okay, so I drew a total of 18 electrons there. So 20 minus 18 gives me 2. So I have 2 more electrons to draw, and boom, on my central phosphorus. Okay, question number 5. Which Lewis structure error makes drawing automatically invalid? Makes a drawing automatically invalid. Showing oxygen with a double bond. Interesting. Giving hydrogen 2 electrons. Ooh, wait a minute. That was something that we know is hydrogen needs 2 electrons. So that answer option kind of off the table. Still unsure about the oxygen with a double bond. Leaving a formal charge of -1 on any highly electronegative element. Now that one goes beyond the scope of our class just a tad. But you could kind of look at that as on your actual exam, that would be kind of a filler answer. That would be something that is obviously correct. And then giving hydrogen more than 1 bond. Okay. Can anyone tell me in the chat, if I draw hydrogen like this, how many electrons does that hydrogen have? Just add that to the chat. 4. Can hydrogen have 4 electrons? No. It can't exceed the octet. So this right here makes that incorrect. So that automatically invalidates that structure. I know that previous answer about formal charges might have been a little bit of a distractor, but it looks like the most popular answer that everyone picked is the correct one, hydrogen with more than 1 bond. Hydrogen always has 1 bond, no more. Which molecule would require the fewest double bonds to satisfy all octets? Okay, so now we've got 3 different molecules. We've got CO2. If we draw CO, you know what? I'm going to go ahead to a new slide. CO2. Okay, so that's 2 double bonds. SO2, well, if you drew that, you'd end up with that right there. That's all 2 double bonds, or that's also 2 double bonds. And then last but not least, C2H4. I know that I drew this molecule at one point. Carbon's rolling in with 4 valence electrons. So 2 times 4 gets us carbon's valence electrons. So that would be 8. Then 1 times 4 is hydrogen's valence electrons, and that would be 4. So we've got a total of 12 electrons to draw. Why does it double bond again? A double bond is formed based on the number of atoms that you can draw. And I'll circle back and draw CO2 in just a moment. But here we have a total of 12 electrons. So if you were to draw C2H4, you might draw something like this: CH. And I'll go ahead and give you answer option A or B as possible structures for C2H4. So if we were to do it like this, let's see, one, two, three. Answer option B. I've got two structures for C2H4. As you can see, that doesn't have that has a complete octet. So that carbon is good. But what about this carbon right here? That's no good. It doesn't have a complete octet. Now, if we look at both of these structures, though, how many electrons have we drawn? 2, 4, 6, 8, 10 electrons. So we've got 10 electrons drawn there, but we have 12 to draw. So obviously there's something more that we can add here, and we add a double bond. Now we've got 2, 4, 6, 8, 10, 12. Okay, there we go. There's C2H4 with total of 12 electrons. Now, this one over here, 2, 4, 6, 8, 10. You know, if I were to put a double bond in this structure on the right, the structure B, let's say I did this right here. Well, now this carbon right here exceeds the octet. And this one still doesn't have a complete octet. So our correct answer is, or our correct structure for C2H4 is this one, A. Now, in addition to that, the heart of this question is which molecule requires the fewest double bonds? Well, C2H4 is the correct answer. Okay. Now, question number 7 reads, which of the following molecules contains exactly 3 electron groups around a central atom? Okay. An electron group, S. Well, an electron group is basically just using the AXE. AX. That's an electron group. That's an electron group. A lone pair is also an electron group. Now, if we look at CO2, we're looking at this right here. That's 2 electron groups. H2O. That's 4 electron groups. NH3, that's 4 electron groups. And then SO2, I drew it just a moment ago like this, but there is also a lone pair of electrons. So there's our 3rd electron group. Now, the next one is, how many lone pairs are on the central atom of the Lewis structure ClF3? Well, Cl brings in 7 valence electrons. F brings in 7 valence electrons. We've got 28 electrons to draw. I'm going to say Cl. Yeah, that's right, 28. F, F, F. Here we've got, see, that is 8, 16, 24, but we had 28 to draw, so there's a lone pair, there's another lone pair. So we had 2 lone pairs on the central atom of chlorine. I'm sorry, I said that I was going to circle back and draw the structure of CO2 on the previous question, and I will do that right now. So carbon rolls in with 4 valence electrons, each oxygen rolls in with 6. So 6 times 2, we've got 12. 12 plus 4, we've got 16 electrons to draw. Okay, so if we do that, okay, and then our next step is to complete the octet for our adjacent atoms. That would get us to 16 electrons. The problem with this structure is that carbon does not have a complete octet, and we don't have any additional electrons to draw. So you could kind of think about this as let's imagine that a molecule doesn't have or has an atom without a complete octet, and we don't have any additional electrons. What we can do is kind of repurpose. We'll erase these two electrons and convert them to a shared pair of electrons. So now we've got oxygen with 8 electrons around it, oxygen with 8 electrons around it, and carbon with 8 electrons around it. Absolutely. I'm happy that I remembered to circle back to that. If there's something that anyone had questions on, please don't hesitate. Okay, now I'm going to end the poll. 3, 2, 1, 0. I'm going to share the poll. And by the looks of it, the first question, hydrogen's correct. 24 is correct for number 2. Number 3, sulfur is correct. Number 4, one lone pair. Number 5, giving hydrogen more than one bond is the correct. I think that if I didn't have this answer option C in there, I probably would have gotten more correct answers. C2H4 is correct. SO2 and 2 is correct for these. Now I'm going to pop up the next questions and I'm going to leave those for you guys and I will be right back. Okay, so get after these next questions. Okay, so I'll start getting after these questions with y'all. Okay. Oh, first one. What is the molecular shape of BF3? Now, if you remember, this is a question that is rooted in molecular geometry. And BF3, if you were to draw this molecule out, it looks like this. That's a molecule that has 3 electron domains. There's no lone pairs on boron because boron does not have to kind of follow the octet rule. And so what that means is that all 3 of these things, this is the AX3 designation. A is your central atom, and X are your adjacent atoms. You have 3 adjacent atoms, no lone pairs. So whenever I say no lone pairs, essentially you could look at it as AXE3, E0, but there's no real point in putting the E0, so I'm just going to erase that. Now, that is trigonal planar. So that means that all 4 of those atoms are on a flat surface, and they're 120 degrees away from one another. So 120, 120, 120. Next up, which molecule is tetrahedral? Well, a tetrahedral molecule, that is where you have 4 things, 4 almost identical things coming off of that central atom. So that would be an AX4 structure. And, well, which of these is AX4? Let's think about it. H2O. Okay. We've got a central atom with 2 adjacent atoms and 2 lone pairs of electrons. So that would be AX2E2. Okay. Then we've got SO2. We looked at that one last time. And this is something that you might see in on your exam where you have kind of a recurring theme of molecules that kind of resurface. That's a very poorly drawn SO2. That would be AX2E1 as the code kind of for that. Then NH3. Ooh, this one's tempting. We've got N, H, 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 and a lone pair of electrons. AX3E. So last but not least is CH4. And that is this. All right. So CH4 is our correct answer. No lone pairs on that. In comparing CH4 and NH3, okay, if we look at these two structures, this question states NH3 has smaller bond angles. So what that means is that the distance between these two atoms, or the angle between them, is lower than these. Huh. The question is why, basically. Why are these right here smaller than these right here? And the answer to that is, well, the difference between them. AX4, so four adjacent atoms, four shared pair of electrons compared to a lone pair of electrons. So that lone pair of electrons, essentially what it does is it pushes with force downward on on the shared pairs of electrons. So NH3 contains a lone pair that repels bonding pairs. Question number 4, what electron geometry is H2O? Okay, so H2O is a molecule that's really tempting to say, oh, well, it's got four things around it. AX4 is tetrahedral. H2O is not AX4. It's AX2E2, and that shows what is known as bent geometry. Because this lone pair right here and this lone pair right here, they also push with force down on those shared pairs of electrons. Number 5. Oh, and actually, I'll give you a couple of other examples. CO2 is a good reference for linear. And then the other option, um, AX3E1, erase that, erase some of these markings that I have. AX3E1 is an example of a trigonal pyramidal. Now, I can almost guarantee you that you will have questions about these geometries. So this would be a good thing. There's a table that I included in the slide deck for this that I would go back and look at those slides and maybe make some notes about those because that will help you. Because remember, you can use a single 3x5 like piece of paper index card sort of thing. Okay. Uh, which central atom arrangement leads to trigonal planar shape? Oh, we're in the lead on that. Three bonding groups or three shared pairs and no lone pairs is the correct answer. That's what we see with BF3. So that question is kind of a redundant question. I've tried to avoid redundant questions, but here I just wanted to doubly emphasize that. Which molecule has a bond angle closest to 180 degrees? We've got CO2, H2O, and H3. And what we're talking about is the angle between these two bonded things. Well, if you were to get what is it called? Compass or something like that, you'd see that this X or these two oxygens are 180 degrees away from one another. Okay, so I'm going to go ahead and close these questions out so we can move on to the next batch of them. So I'll give you another 5, 4, 3, 2, 1, 0. I'll share the results. And what we've got is For the first question, trigonal planar. Second question, tetrahedral. Third question, NH3. Fourth question, bent is correct. Fifth question, three bonding groups, zero lone pairs. Sixth question, oh, that was great. 92% of you got that is CO2. So great job there. We'll move on to the next batch. And now I'm also going to give us a new slide to work on. So these are questions number 45 through 49. Oh, dang it, Joel. You know that. Stop sharing. And that's done sharing. So now I should be able to launch in just a second. Launch. Okay, so 45 through 49. Which molecule is nonpolar overall? Okay, so now we're talking about polarity of molecules, but we also need to remember polarity of bonds. What is that rooted in? Polarity of a bond is based on electronegativity. Could anyone add to the chat, what is the most electronegative element? F, perfect. Now, one thing that I want to stress is whenever I say fluorine is the most electronegative element, that is not like, oh, fluorine is the most except for the noble gases. No, fluorine is the most electronegative element. Now, the reason for that is because it really loves to have electrons. So when it's sharing electrons, it really loves to kind of take them on the most. Well, your noble gases don't like sharing electrons, so they're less electronegative. They aren't even really considered in terms of their electronegativity. So don't think, oh, I gotta, fluorine is the one that's commonly. No, disregard those noble gases when it comes to electronegativity. Um, okay, so which molecule is nonpolar overall despite having polar bonds? How can that happen? Well, I always kind of think about a molecule is like a little game of tug of war. We've got a polar bond where we've got differences in electronegativity. We've got a molecule that is going to be polar or nonpolar. Now, we've got H2O. Spoiler alert, this is a polar molecule. So to answer this question, do we have to even get into if this is a polar bond or not? No, we don't. Because the presence of this lone pairs of electrons, AX2, E2, that structure right there with the lone pairs is going to make this molecule a polar molecule. NH3. Well, that looks like this. AX3E. Therefore, this is also, with a lone pair of electrons, this is also a polar molecule. Then, last but not least, is CO2. Okay, so CO2, when it comes to electronegativity, and the structure of this molecule, nonpolar overall, despite having polar bonds. Okay, so let's think about this. I will give you electronegativity values in the questions. Carbon has an electronegativity value of 2.5. Oxygen is 3.5. Okay, so the difference there is 1. So 2.5 minus 1.5. So, well, CO this is a polar bond. This is also a polar bond, but this is a game of tug of war. And so they basically cancel one another out. So CO2 is the correct answer. HF, well, that's also a polar compound. So you kind of just say, well, yeah, that's also invalid. So there's kind of two different ways to approach some of these problems. Which bond is the most polar based on electronegativity difference? Now, I would say the easiest way to approach this question is to think about these atoms and think about how far they are from one another on the periodic table. Again, I will give you the electronegativity values. The two most popular answers are HF and LIF. And let me tell you, those are the two most electronegative, or the two that have the greatest differences in electronegativity. Now, this is a question that H has an electronegativity value of 2.1 and Li is 1.0. So if you're like, oh man, I picked HF instead of LIF, You're on the right path because could somebody add to the chat what is the electronegativity value of fluorine on our Pauling scale of electronegativity? Victor, you're absolutely right. It's 4. So we're looking for the greatest difference. So the correct answer for this is LIF. But again, if I gave you the electronegativity values as I will on the exam, you'd be able to answer that. I'm fairly confident of that. So LIF is the correct answer. Number 3, what feature of a molecule most strongly determines whether dipoles cancel? Ooh, we just looked at this. CO2 as an example of dipoles or polar bonds canceling. And the correct answer to that is the shape, the molecular geometry. So if the geometry has the two bonds directly opposite one another, they'll cancel out. So that is the correct answer. The size of the central atom doesn't really impact it. Whether the molecule contains hydrogen also doesn't really impact it. Number of bonds also is not going to be a big contributing factor. Which molecule must be polar? Okay, so CO2, that's a linear molecule. That cancels. CF4, tetrahedral. No matter how polar those bonds are, they're going to cancel out. BF3, those are 3 bonds that all cancel one another out. And then H2O, that's our only polar option because it is the only one with lone pairs of electrons on our central atom. Number 5, which molecule is guaranteed to be nonpolar? Okay, so in order for this to be nonpolar, we've got to have, what questions am I looking at? I'm looking at the poll questions, final exam review questions 45 through 49. So if you're on your phone or a mobile device, you want to tap more and then go to poll, and that's where you'll see these questions. I just got a private message question about this. Do you see those? Person who messaged me? They are up now. Yes. Okay, so which molecule is guaranteed to be nonpolar? We've got PF3. Mm, PF3. We drew that one a little bit ago, and with that, look at this. We got a lone pair of electrons. So that is a polar molecule. SO2. Well, I drew SO2. What does SO2 have? Lone pair of electrons. CH2Cl2. Ooh, this is an interesting one because that's kind of like C2 or um sorry, CH2Cl2. If I were to draw that, it would look a little bit like this. Um, we've got, oh, let me erase that. Cl. We've got 4 different things coming from a central atom. Well, 2 different things. And as a result of that, we're looking at something that is not, or that is going to be polar because it is not symmetrical. Whereas CF4, the electronegativity differences between carbon and fluorine, yeah, they're pretty stark. That makes these bonds polar, but they all cancel out. Whereas if you look at CCl and CH, well, one of these bonds is more polar than the other. Okay, so I'm going to give you another couple seconds to answer these questions. Okay, cool. And I'm going to end this poll. 5, 4, 3, 2, 1. All right. So looking at each of these questions, which molecule is nonpolar overall despite having polar bonds? CO2. Correct. That was the most popular answer. Next up was, again, I mentioned that would have been a question that I think everyone would have, or at the very least the HF folks probably would have gotten right because they would have had the electronegativities on the actual exam. I'm sharing the results now. Sorry about that. So question number 1, CO2. Question number 2, LIF. Question number 3, molecular geometry is going to be a big determiner, determining factor for um, polarity. Number four, which molecule must be polar? H2O. Number five, CF4. If you have four things coming off of a central atom and they all cancel out, or sorry, and they are all identical, they're going to cancel out. So that's going to make that molecule nonpolar. Okay, I'm going to stop sharing. I'm going to go back. And now, if you've missed some of the questions, I'm about to open up the next 3 or 4 questions. So get ready for that. And again, if you're on a mobile device or on a tablet or something, you might have to hit the 3 dots, the ellipse that says more, and that will pull up polls, or that will pull up a menu. And on that menu, you'll find polls. Okay, POLLS. So launch. Next up, final exam review, 50 to 53. Which molecule exhibits hydrogen bonding? Ooh, okay. Hydrogen bonding is a specific type of bonding. And hydrogen bonding, what do we need for H bonding? First and foremost, we need hydrogen. Could anyone tell me there's 3 other atoms that we need in order for hydrogen bonding to exist? So I'm going to say hydrogen plus, I'll give you a little bit of a starter. Nitrogen is one. And then what are the other 2 atoms? Oh, Victor, coming through. Well done. Oxygen or fluorine. So we need to have hydrogen and nitrogen, oxygen, or fluorine. So we need to see those. So if we look at CH4, does CH4 have hydrogen? Yes, it does. So I'll make a little table here. HCl, CO2, and HF. Let's see. If we don't have hydrogen, then we can't have hydrogen bonding. CH4 has hydrogen, but no on everything else. HCl, that says HCl, not ACL. I'm not talking about a ligament. Yeah, HCl has that, but nothing else. CO2, huh? It only has oxygen. It's not, no dice there. HF, check and check. So HF is our correct answer there. Which substance boils at the lowest temperature? Okay, so when it comes to a physical property like a boiling point or a melting point. So boiling point, think about what happens when something boils. What state does something have to be at, and then does it transition to? Add it to the chat. And you can use the single letters to indicate them. Yeah, a liquid to a gas. Okay, when something goes from a liquid to a gas, the change is it boils. Okay, so we've got H2O, NH3, HF, and CH4. Let's think about this, and let's actually apply hydrogen bonding, because it's those forces that hold these things together that determine if, or that influence physical properties. So if we have hydrogen bonding is it's one of those weak but strong weak forces. Does anyone remember what those are called? And you can use the 3-letter code or 3-letter identifier acronym for them. It's actually kind of in the next question, question 3. Intermolecular forces. Okay, so your weakest intermolecular force is dispersion forces. The strongest intermolecular force is hydrogen bonding. So if something has hydrogen bonding, it's going to require more energy to actually disrupt it. So I'm going to go ahead and give a little table. H2O, NH3, HF, and CH4. So we could look at this table and say, does this have hydrogen bonding? Does H2O have hydrogen bonding? Yes and yes, because it has the 2 requirements. Does NH3 have what is needed for hydrogen bonding? Yes, has hydrogen, and yes, it has nitrogen. HF has hydrogen and has fluorine, so it's capable of hydrogen bonding. CH4 has hydrogen, no N, O, or F. So no H bonding. So that means CH4, did I say CHF? I'm sorry, I meant CH4 is held together by really weak forces. So the substance that's held together by the weakest forces is going to have the lowest boiling point. So I'll say lowest BP because of weak, weakest IMF. Okay, which type of IMF is present in all molecules? Oh man, hydrogen bonding. Here we can already see that not hydrogen bonding is not in everything. Dipole, dipole, ion dipole, and dispersion. Okay, dipole, dipole is when you have two polar molecules. So if you had something like um, H2O and let's go with NH3. No, not NH3. I don't want to do that. Let's go with H2O and yeah, I'll go with C2 or CH2Cl2. Okay, so this right here is capable of hydrogen bonding. This is not capable of hydrogen bonding. You would see dipole, dipole. So two polar molecules that interact with that. Now, if we had instead of C2 or CH2Cl2, we had, or instead of H2O, we had Na plus. That's an ion plus a dipole. Okay. Last but not least, so last but not least is dispersion forces. These are the forces that hold everything together. They're the weakest of the intermolecular forces, but they're the type that hold them all together. Which molecule has the strongest dipole-dipole forces? Okay, so in order for this to be true, we have to have two molecules that are polar. Is CO2 polar? Give me a Y or N in the chat. Is CH4 polar? Y or N in the chat. Nope. So could CO2 or CH4 participate? Do they have the polarity to interact in dipole-dipole interactions? No, they don't. So those are out. SO2 and N2. Well, let's think about, is N2 symmetrical? N2 looks like this. Yeah, it's symmetrical. And the polarity of the bond, yeah, that's out. Um, then last but not, so that's a molecule that is basically, yeah, that's a that is, sorry, I got distracted by something. That is a molecule that is not on the table as having dipole-dipole interactions. SO2, however, is. That is capable of dipole-dipole interactions. And so that would be your strongest. Okay, I'm going to end this poll. Give me 10, 5, 1, and I'm going to close it off. All right. I'm going to share the results. I think, again, most popular answers shown through HF, CH4, dispersion, and SO2. We're good. Those are all of them. I'm going to go ahead and stop my share. And then I'm going to go over to launch 54 through 57. And I'm going to give you guys some time to work on those because I got to do something in the background. Okay. So, question number one. These are gas law related questions. A gas has a volume of 3 liters at 1 atmosphere and 300 Kelvin. What is its volume at 2 atmospheres and 300 Kelvin? Okay, so the only variable that changes here is pressure. So this is a question of, well, what happens to the volume? So if we remember the relationship between pressure and volume, when we talked about that, if you increase the pressure on something, what's going to happen to that volume? That volume is going to go down, provided that all other things remain constant. And we can effectively look at this as an equation that is our pressure over our volume, or pressure times volume, is equal to pressure times volume. So our pressure is 1 times 3. We're going to set that equal to 2 times blank. Well, 3 equals 2. I'm just going to call this 2 times V. Divide each side by 2, and you get 1.5 is equal to V. Question number 2. A 0.5 mole sample of gas occupies 12 liters. So N, if you remember, that's the value that we use, or that's the variable that we use to define the amount of a gas. Then we've got V, which is our volume, which is 12.0 liters. Our temperature is constant, so we don't need to worry about anything else like that. Now, what would 1.5 moles of gas occupy? So if we think about this simply from the perspective of we have a balloon and we've blown a little bit into it. We've blown 0.5 moles of gas. It doesn't really matter for our purposes what that gas is. Instead, just think about it from the standpoint of if I added more gas, what's going to happen to the volume? The volume's going to go up. So when we do that, we can immediately eliminate 4 and 8 as answer options. In this case, we've tripled it. So I'm going to say N over V is equal to N over V. And this is N1 V1 is equal to N2 V2. So 0.5 over 12 is equal to 1.5 over V2. So what I can do is cross multiply and then divide. So 1.5 times 12 is 18, divided by 0.5 is going to give me 36. You could also kind of look at it as, well, I tripled it. I tripled my amount of gas. Therefore, I want to triple my volume. Okay. Question number 3. Which of the following changes would cause the pressure of a gas to double if our moles are kept constant? Okay, so which of the following changes would cause the pressure to double? We could either cut the temperature in half, double the temperature, double the volume, or triple the temperature. Okay, we're anticipating doubling. So I would eliminate triple the volume as an answer option. Then I would think about, okay, well, what am I looking at in terms of the relationship between pressure and temperature? Because pressure goes up times 2. If I cut the temperature, what would I expect the little gas molecules to do? They're going to slow down. The number of collisions are going to be lower. So the pressure in that vessel is going to go down. if my temperature got cut down, cut in half. That's not what I'm looking for. I'm looking for what is going to cause my pressure to double. So answer option A. I'm just saying temperature goes down, answer option B and C, 2x the temp or 2x the volume. I'm going to eliminate A as an answer option. Now I'm down to B and C. Answer option C is if I doubled the volume. Okay. I always think about pressure. I try to personify it, or one of the things that I like to do is try to personify it. Um, so let's do that. Let's say that you've got people in a room. And let's use pressure. Think about pressure as like stress. You got two people in a room. If you made the volume go down, those people are now in a smaller space. So they're going to be stressed out. So the pressure is going to build. Okay. So if the volume goes down, then the pressure goes up. Those are inversely related. Answer option C says, well, we double the volume. Wait a minute. So what that means effectively for this example is we took the room from being this size and we doubled it. I'm going to change colors for this, and the room is now this big. Not drawn as well, but it's that big. Are those people happy? Are those people less stressed? Yeah, they're a lot less stressed. They have a lot more room to work in. Okay, so C is out. Answer option B, we double our temperature. That's all that's left, and that's our best answer. Then, number 4, a gas at 200 Kelvin and 2 atmospheres expands until its pressure is 1.2 atmospheres at the same temperature. What happened to its volume? Okay, so its pressure is the pressure is going down. So the pressure goes down, the volume increases because this is our relationship between pressure and volume. If the volume goes down, the pressure goes up. If the pressure goes down, the volume goes up. Or in order for the pressure to go down, the volume has to go up. So I'm going to end the poll here. I'd like to share the results. We've got one more batch of questions, and then we got an extra credit opportunity. So I need y'all to hang around for that. Our most popular answer for number 1, 1.5, that's the correct answer. Number 2, 36, that's the most popular answer. That's the correct answer. Number 3, doubling the temperature, that's the most popular and correct answer. And number 4, volume increases, that's the most popular and the correct answer. I'm going to stop the share. And I'm going now to the last batch of questions. Oxidizing and reducing agents. Okay, the first question reads, you've got solid Zn plus Cu2 plus yields Zn2 plus Cu. Which species is oxidized? Well, which is the species that loses electrons? We're reading from left to right. So zinc, Zn, is oxidized. It loses electrons. Therefore, what gets reduced? Cu2 plus gets reduced. It gains electrons. Question number 2, which statement correctly describes hydrogen ions reacting with a metal above hydrogen in the activity series? Well, H plus a metal, I'll just say zinc, is going to lead to H2 plus Zn plus. So the hydrogen ions get reduced and they form H2. According to the activity series, which metal will react with magnesium in solution? Now, I'm not going to ask you on the exam to memorize the activity series. The questions that you should anticipate on the activities related to the activity series are going to be in terms of where are these different things positioned? The things that are higher or lower. Okay, which metal will react with magnesium ions? The correct answer there is zinc. Zinc and lithium are pretty much at the top of the activity series, so they will most easily be oxidized. again, I'm not going to give you the activity series, but my questions about the activity series are all kind of conceptual. Now, I want to go back to this first question before I close this out and then switch over to the extra credit thing. Um, when you look at this sort of question at the top, and I'll go ahead and I'll leave the poll going. I'm not going to share the results. All right, zinc is correct. H plus gets reduced to form H2 and zinc. Okay, so in terms of this reaction, what I want you to know is I want you to be able to say that zinc gets oxidized. Then I'd like somebody in the chat to tell me, does that mean that zinc is the oxidizing agent or is it the reducing agent? Is it the OA, the oxidizing agent, or is it the RA, the reducing agent? If it gets oxidized. When something gets oxidized, it is the RA, the reducing agent. The way that I always kind of think about it is, I like to personify it. Me, or whatever. I have electrons. I'm going to lose those electrons. And whenever I lose those electrons, I now have an overall positive charge. This shows this person getting oxidized. Gets oxidized. Now, why is it the reducing agent? Well, those electrons were lost to something else. If I added, let's say, Ag plus, silver ions, well, I would give those electrons to this silver ion. I got oxidized, but in the process of me getting oxidized, I reduced. I made this other thing get reduced. So the thing that gets oxidized makes something else get reduced. Could everyone give me a 6 in the chat if that makes sense? Okay. Now the opposite is true. If you get reduced, then you cause something else to get oxidized. So that's why if you get oxidized, or if you get reduced, you are the oxidizing agent. The way that I try to simplify it for myself also is just to say, okay, well, I'm going to identify whatever gets oxidized. That's my RA. The thing that gets oxidized is the RA. The thing that gets reduced is my OA, my oxidizing agent. Okay, I'm going to give you another 5 seconds on these poll questions. 3, 2, 1, done. Okay, now what I'm going to do is we've got good. We've got roughly 15 minutes left. Now, with that time, I'll keep those annotations. What I need you guys to do is go to your Canvas page. Your Canvas page has a couple of extra credit opportunities for you. I'm going to go ahead and stop the recording now, though, because the recording